Hello friends. This is part of the Miller, Ranch-Baran, Belitsky, and Deaver production company. This feature is where quality and education meet and the enrichment of your life begins.
Okay, I'm going to talk about the capillary rheometry today, and this is a part of your fourth lab report. As you are aware of the situation now, we are going to submit some video and lecture online. Even for the lab, you will receive some type of lecture regarding how to do the experiment or how to provide your report. Actually, I'm going to eliminate the last lab report, so you are going to finish only one more lab report, which I provide for DSC, diffraction scanning calorimetry, and TGA. So today, I'm going to explain a little bit about the capillary rheometry, and some of you already finished the capillary rheometry. For those who haven't finished, those experiments, so I'm going to explain it today and send you a few minutes of video. So here you have a capillary, and the concept and theory is that we apply load or force the material, and we measure shear stress versus viscosity and shear rate versus shear stress and shear rate versus viscosity. So this is the equipment and theory that we are going to work on it, and the machine that you will see in the next video. It works based on the pressure and some type of sensor, like a pressure sensor and a temperature sensor that you measure pressure and temperature. And then, as you can see, by applying the load or force, we push the material into the barrel and finally the die and nozzle. Then we measure shear rate versus viscosity and shear rate versus shear stress. Basically, the machine is doing it for you. So, but in order to understand what's the concept behind the machine, this is the formula and the graph that you will see. So, in general, you have Newtonian fluid and non-Newtonian fluid. For a Newtonian fluid, you have a constant viscosity versus shear rate, and for non-Newtonian, you have a nonlinear function. So this is the concept of regarding the material that you are going to test. The machine that we are using, as some of you already know, that the different part of those elements that you can see is based on the software that we will run the test, like polyethylene and polystyrene at constant temperature, and we measure shear rate and shear stress. So this is the windows for the machine that some of you are familiar with. And when we run the test, we collect the data from the barrel. So what the machine is doing, actually, by sensor, collect track the data like 10 point or 20 point each second, and they put in the file, and then it will give you a graph based on the data that you have, and then you can have the shear rate versus shear stress or shear rate versus viscosity. And if you want to get the point how the barrel and die works, actually there are different die for the capillary rheometry with different diameter and different die length. So this is a general concept of the capillary rheometry. So this is the die length, and this is die diameter, and this is very similar to the extrusion and the extruder that you are doing in the polymer process. So what we are getting actually the pressure and there's no die length. So if you start to push the material, so you're pushing the flow for polymer melt inside the bottle and finally the die, and you have a material that's coming out of the die, and by this way you're measuring viscosity versus shear rate or shear rate versus shear stress. So this is the concept of the capillary. And the formula that you have, if you want to know the theory behind this, so we are dealing with the shear rate calculation and for Newtonian and for non-Newtonian. So when you are dealing with the Newtonian, we are dealing with the shear rate, and for the non-Newtonian, we are dealing with the average shear rate. But both are same concept. They are the same. In this formula, you have pressure and flow rate, which is related to shear stress of the wall. So if you want to get the sense what is the theory and formula behind this, you can see it from those formula. For any capillary rheometry, you have this type of graph. When you are doing a test for any capillary rheometry, we measure shear strain versus viscosity, or we measure shear rate versus, shear stress and viscosity for different type of the material. And as you change the temperature, actually in this experiment we are doing constant temperature, but you can change the temperature. By changing temperature, you can see variation of the shear rate versus viscosity. So this is typical graph for any material that you are doing. For example, for polyethylene or polyester, we would see the same path, same graph, of course, different value. And this one is relation between shear viscosity and shear rate, similar to this one. This one, is relation between shear stress, which is y-axis, and shear rate. So as you can see, for any type of the polymer melt, when you increase shear rate, viscosity is decreasing. But when you increase shear rate, your shear stress is increasing. So this is a relation between viscosity shear rate and shear stress shear rate. This is general, typical graph for any type of polymer melt rheology. So the main concept and key point for that experiment is relation between viscosity shear rate and shear rate shear stress. So this is the key point for that experiment. The next step is we'll show you some type of how to do the experiment, and in terms of the, to get the data and provide your report. So this is part of your fourth report, and next we will go to the dynamic rheometry, which is maybe next day. Okay. Thank you.
I'm going to explain to you guys how to use the Capillary rheometer. First, we're going to go over what's on our monitor here, how to set up our test, and what the test is specifically going to do. And then from there, we'll move over how to actually use the rheometer itself. All right, so here we have a monitor. We have a way to start a new test. So we'll go ahead and click New Test. So we're going to be using the long die at a constant shear rate test. I'll show you guys what the die looks like. Here we can define our test. So our pre-test, we're going to do a compression and preheat. So essentially what the compression will do is that the piston is going to move down at a rate of 75 millimeters per minute. It's actually really slow until it reaches a pressure of at least 250 psi, and that's going to preheat for 5 minutes. Go ahead, OK that. Our temperature, our top, middle, and die temperatures are all going to be 230 degrees Celsius, and that we use that for the ASTM standards. Go ahead, OK that. here you can see our different stages, starting from stage 1 going down all the way through 10. It's going to start at a pretty low speed at 3.33 millimeters per minute, and then once it reaches a point that the machine defines as equilibrium, which is essentially when the pressure levels off as it's moving at that speed, it will increase to the next speed, and that will be 5.15 millimeters per minute, and then 7.95, and then it keeps going up until it gets to 167 millimeters per minute, and that's our 10th stage. So once the test is set up, we can go over here and click Run Test, and that would immediately start the test. As you can see, we have our temperature at the top is sitting nicely at 231 degrees. Our middle temperature is at 232.9, and our die temperature is at 232.1. That's just because it overheated a little bit, and that's not really a big deal. The pressure reading isn't accurate. There's no pressure at all because the piston isn't even in there, and there's no material either. The volume of our barrel is always 39.41 cubic centimeters, and that's we sort of always just fill it to the top, and I will show you guys how to do that. Alright, so in this sort of special looking briefcase, we have our tools that we'll use for the capillary rheometer. Let's take a look inside. So here we have our little toolkit. Right here we'll use this to load our material into the barrel. Here's our cleaning rod. If you remember from the melt flow indexer, it's pretty similar, it's just bigger. This is our loading rod. We use this to put the dye into the barrel. Here we have another cleaning rod. These little copper or brass brushes, I don't know what they are. They just screw in there, and we can use that to clean out the barrel when it becomes too much of a mess for whatever reason. We have a few other tools in here that we won't really be using, so we're just going to skip over those. In here we have our dies. So these are the two dies that we're not going to be using. This one's actually rather small. You can see that the die is inset in the die holder. The rest of them aren't exactly like that. Go ahead and pop that back in. Here's our largest die that we have. It's about an extra third of the length compared to the die that we will be using for this test, and this is its die holder. And then this is the die that we will be using, the 2x36 by 180-15. You can see that it's been used quite a bit. So we're just going to go ahead, try not to drop these. As with the melt flow indexer, the dies are made of tungsten, so we got to do our best not to drop them on stuff. The die holders, however, I don't believe are tungsten, but we still need to be careful with them. This is our massive Allen wrench that we'll be using to install the die holder. Alright, so this is our capillary rheometer from Malvern and Roseanne. So essentially how it works is this thing will slide over, and here's our piston or rod. It just goes in here and screws in up to that top portion. I'm not going to screw it in yet, but it screws into that top portion, and this is just one giant pneumatic piston. It might be hydraulic actually, but what it'll do is it will just drive the piston down into our left barrel here, which is already heated, and I'll push the material out of the bottom through the die, very similar to the melt flow indexer. The die will be installed down here. This helps measure die swell as well as the rate in which it's flowing out of it. It's not super important, but if you're wondering what that is, that's why it's there. Alright, so we're going to install our die holder, which is just this thing. And it's going to go right here, and this is our left barrel. I'm just going to essentially put it onto our giant Allen wrench, screw it in. And everything on this machine gets hand tightened only, just essentially until you can't do it, but not so tight that we start ruining the machinery. So we're going to install the die. We're going to put it into our preheated left barrel. Just going to drop it in. Assuming it doesn't get stuck on stuff, I'm just going to push it out. So we're going to go ahead, we're going to load our material. This is polyethylene, specifically high density polyethylene. I'm just going to take a scoop into the beaker. Spilled some. Okay, just going to pour it in. If you're wondering, the immediate area is indeed very hot, even in the air. Alright, so now we're going to install our piston. So all we have to do is just rotate this over until it stops. Drop this in there a little bit. Screw it on. And like I said earlier, everything on this machine gets hand tightened. See, it's already picked up some material because it's heating up very quickly. So we're going to start the test soon. Alright, so we're just going to come over here. All we have to do is click Run Test, and we'll start the test. So now that we started the test, it's doing its compression. It's waiting until it reaches its 250 PSI, which is slowly going up over here. We're at about 160 right now. Once it gets up to that point, it will preheat for 5 minutes, and then it will continue with the test. Alright, it's almost done preheating. We got about 20 seconds left. It's sort of just holding the piston with a constant pressure. The pressure is sort of going down right now as material is currently leaving the barrel. But when it's done preheating, it will start its first stage at 3.33 millimeters per minute. There's really not much for us to show you of that because it is indeed incredibly slow. Oh, now it's just started its first stage. Now you can see here it says it's waiting for equilibrium. So essentially it's going to wait for, as the speed is increasing, it's going to wait for the pressure. It's going to wait for the pressure to stop increasing. All right, so we're already in stage 9 now. Now stage 10, and you can see it's extruding the material quite quickly, and we're getting a nice little spiral of molten plastic, and it just stopped. All right, now that the test is over, we're going to come over here. I'm just going to click Analysis. It's going to give us our data. So, here we have our plotted data points. This probably looks a bit like this at the beginning, which is not normal, probably because I sort of put the die in and then immediately started the test, so the die probably wasn't heated all the way. But you can see that they're quite reminiscent of each other. This is our shear stress, which is shear rate, and here we have our shear viscosity, which is shear rate. And the shear viscosity and the shear stress are inversely proportional to each other. So that's why the graphs here sort of mimic each other in a way. Here we have our general downward slope. Here we have a general upward curve. And here we also have our pressure. Essentially, we just have our pressure, shear stress, shear rate, and shear viscosity at each speed that it was going at, so 3.33 or 5.15, all the way up to our 167, as well as the time that had occurred during the test. Just so you guys know, all the data from the capillary rheometer is not collected. You're not going to need it for your lab reports. Dr. Rajbaran's going to have you guys writing in a little bit of a different format for the time being.